Welcome back. Good morning. Last time we started on Unit 7, which is a recap and a little bit of new stuff into the frequency response of LTI systems. Okay, let's go to the Oracle, the PowerPoint. I think we left off here last time where I started talking about the 8 basic ingredients in an LTI transfer function. They were, again, gain, differentiators, integrators, real zeros, real poles, and complex conjugate zeros, and complex conjugate poles, and pure delays. Okay, so those are the 8 possible things you can have in an LTI transfer function. That was in the Laplace version. In the Fourier version, so if we're assuming causality, so assume causal, then we just get to plop in a j omega everywhere we see an s, and we get the frequency response, a big H of omega. And as you can see, it has the same ingredients, right? The gain is still there, the differentiator is still there, the integrator is still there. It's just now in terms of, instead of s's, it's j omegas. So what else would I like you to see? Well, okay, if we're going to square stuff like this, then that turns it from an imaginary number into a negative real number. And so that's what's going on in the next slide. I'm doing that, so that's where this negative sign comes from. But I'm also factoring out a bunch of stuff from the top and the bottom. So if you'll recall in the last slide, this thing was written as j omega plus z sub I. Well, if you pull out the z sub I, you will get something that looks like that. And so what I've done is I've folded all of the z sub i's into what I'm calling k prime, right? Because this is all a product. If I factor out one thing from any of these products, that means I can bump it out to the constant out in front. And so this is what I think that you learned is called leading ones form. So it's a 1 plus a function of omega. Here's a 1 minus some other stuff plus a function of omega. Of course, the ones that you can't write in leading ones form are the poles and zeros at the origin, the constant, and the delay. But everything else you can write in what's called a leading ones form. And the idea here is that if you write them in leading ones, then when omega goes to 0, this thing just looks like 1. When omega becomes very large, this thing looks like j omega. So it makes the sketching rules easier to apply. Questions on this slide? Or how we got here from the last slide? Okay. So again, the frequency response of a system is generally decomposed into its magnitude and its phase. And so what I'd like to do is I'd like to spend a little bit of time talking about the magnitude and how we can build up the magnitude of h. Oops. How we can build up the magnitude of h if we know the magnitudes of all the other things. Okay. So certainly, if I want the complex magnitude of a number, and that number is the product of a bunch of factors, then the magnitude of the whole is the product of the magnitude of the factors. So that's why I can move these bars in onto every single factor. What else are we seeing? Well, these guys are special because the magnitude of j omega, the magnitude of j omega quantity to the power m0 is the same as the magnitude of j omega to the power m0. And that's not generally true when you have a function 1 plus j omega something. Okay. Yeah. But the problem is that if I have a transfer function with a bunch of poles and zeros, I could draw each of these things, but it would be really hard for me to multiply them graphically, especially if I've got multiple things active at a certain point in the frequency domain. If I've got one function that looks like this, and the other function that looks like that, and another function that looks kind of like that, those are all really hard for me to multiply together, right? Because what does it mean? Is this thing growing twice as big as those are growing? It's difficult to combine these when they are multiplied. So that's where logarithms come into play. Because if I can take the log of a magnitude, and that magnitude is the product of things, then the property of logs says that the log of a product is the sum of logs. And so that's the whole idea, is that we're going to turn products into sums. So now the log magnitude of the frequency response is the log magnitude of the constant plus the log magnitudes of the things on top minus the log magnitudes of the things on bottom plus the log magnitude of the delay term. So we're gonna look at each of these in turn and see how we can plot them. Because once I know how to plot, say, this, and I also have this kind of term, now I can add these no problem, right? I just shift this up to here, and I do something like that. So adding graphically is much easier than multiplying graphically, especially when you've got lots of graphs that you're trying to combine. So this is the primary reason why we talk about logs in the magnitude of frequency domain rather than just straight up the magnitudes. And then for historical reasons, if you want to turn these into decibels, you multiply everything by 20. Okay, so this thing is what I'm going to write as magnitude h measured in dBs. Okay, so that's my shorthand. Vertical bars with a subscript of dB means take the 20 log of the magnitude of this thing. If you want the complex angle of a product, you don't have to resort to logs or any kind of trickery because the phase angle of a product is already the sum of the constituent phase angles. So there's no need to resort to funny business. So the phase of the top is the phase of the left is the phase of the top, this and this, minus the phase of the bottom, plus the phase of the delay term. Okay. What else can we see? We see that the phase of j omega to the m0 is the same as adding the phase of j omega m0 times, which is why I can write it like this. M0 multiplies the phase. Okay, so now what I want to do is I want to go through and derive or refresh your memory on the derivation of the Bode plots of each of these ingredients, because we've seen that if we know the Bode plot of each constituent, of each ingredient, then we can add them to get the Bode plot of the overall transfer function. Okay. So when we talk about the magnitude of H1 of omega measured in dBs, well, that's 20 log the magnitude of k. There is no dependence on frequency here, so we can call this the log omega axis, and then whatever k happens to be, it will be plotted as a flat line up here. Okay. So this line lies at 20 log the absolute value of k. And it goes over all frequencies. The phase is subtly tricky. So the phase angle of H1 is simply the phase angle of k. And so I think that at first blush, we would all say this is 0 degrees. So again, I'll draw the log omega axis here. But if k is positive, then you're right. The phase angle of k is 0. So we get this. However, if k is negative, then the phase angle is plus or minus 180 degrees. So I'll draw it as negative 180 degrees. Okay, so that's the only subtlety that I want to point out here, is that the magnitude of k doesn't care about the sign, SIGN of k, but the phase angle does. So if you, for any reason, have a negative constant out in front of your transfer function, just realize that it is contributing 180 degrees of phase to the whole enchilada. Okay, let's talk about a differentiator. So what does the magnitude of this thing look like? The magnitude of H2 in dBs is simply the 20 log of the magnitude of j omega. Okay? The magnitude of j omega is simply omega, because j omega is the phasor that points due north, right? That's the j introducing that rotation. So this is just the same as 20 log omega. And if we're only looking at positive omegas, then we can write this as 20 log omega without the bars. Okay. And we are looking at only positive omegas because we are plotting this against the log omega axis. And log omega is only well defined for positive omegas. So implicit in all of this is that we're only drawing positive frequencies, but that's not a whole much of a loss, because we know that Fourier transform for real valued functions is conjugate symmetric. Okay, so if I know the magnitude and phase for positive frequencies, then I can derive the magnitude and phase for negative frequencies if I so desire. Okay, so I want to point out a feature that has been right in front of you for as long as you've seen Bode plots, but you may not have been shown. And that is, why do we plot these as lines when there's logs all over the place? And when I first learned about Bode plots, I just learned the rules, and then I was fine with that. But once you think about it a little bit more, you get, I mean, this happens with any topic. You think you learn it, then you think about it a little more deeply. You realize you don't actually know what you're doing, and then that forces you to learn it again or learn it more deeply. So this is what happened when I came across Bode plots for like the second or third or fourth time, is it finally the light clicked as to why these look like lines. And that's because this is the vertical component. This is the thing that we're plotting. So that would be, I could call it y. This is the same as the name of our horizontal axis. So I could call that x. And so what I'm doing here is I'm saying that the dB magnitude of this transfer function has the form y equals mx. Okay? So when you think about it that way, this is clearly a line with slope 20. That's kind of cool. So where there are lots of lines with slope 20 that I could put on this graph, I need to know one more point. I need to know maybe the intercept. So this has a value of 0 dBs when log omega equals 0. So that would be somewhere like here. And what frequency has a log of 0? What number, when I take its logarithm, doesn't matter what base, do I always get 0?
Oh, 1.
1.
Yeah, so this is 1 radian per second. Good. So this is now a slope of 20 passing through this point. Okay, so this really made things click for me, viewing this as a y equals mx plus b kind of operation. But there just happens to be no y-intercept here, or the y-intercept is 0. Okay. So you'll see this horizontal axis written in a couple of ways. You could see it written as 1, 10, 100, that kind of deal, because implicitly these are log-based 10s. You can also see them as things like 10 to the 0, 10 to the 1, 10 to the 2. So I'll switch back and forth. I think I prefer this because it's got this counting, and I like the counting, the 0, 1, 2 business. But you just have to remember that 10 to the 0 and 1 are the same thing, and sometimes that throws me for a loop. I'm not ashamed to admit. Okay, so questions on the magnitude plot? If we're talking about phase, the phase of H2 is going to be the phase of j omega, but we've actually already kind of talked about that. This is the phasor that points 90 degrees north for all positive frequencies. This is 90 degrees, provided omega is positive. Okay. And we're only looking at positive omegas, so that's your answer. This is going to be plus 90 degrees over all frequencies. All right. So if you can do a differentiator, you ought to be able to do an integrator. Let's talk about that. The magnitude of H3 in dBs is the 20 log of the magnitude of 1 on j omega, which is 20 log of magnitude j omega to the minus 1, which is 20 log of magnitude j omega to the minus 1. And now the log of something to a power, that power can come out in the front. So I'm going to do that here. I'm going to take the negative and write it out here, and I get log magnitude j omega. So I did that because this looks like the differentiator case. The only difference is the sign, the SIGN on the slope here. So that means, that's why I say, if you can sketch a differentiator, you can sketch an integrator. It's because it's just the flip. Still crossing at 1 radian per second, and still with a slope of 20, but this time a negative 20. We call it dBs per decade. And then for phase, actually the same kind of analysis holds. The phase of H3 is the phase of 1 on j omega. So this is going to be the, well, there are a lot of ways to do this. You can say it's the phase of j times negative omega, if I multiply top and bottom by j. So that gives me the phase of negative j over omega, which is negative 90 degrees, assuming omega is positive. Okay, so I do these in these pairs because differentiators and integrators are opposites in their name, in where they lie in the transfer function, and in their Bode plots. Questions on these two? All right. If we want the magnitude of what I'm going to call a first order 0, or sometimes called a real 0, then I need to find this thing in dBs. So I'm going to need a little extra space here. So I'll start up here, and I might take the whole margin here. So magnitude of H4 in dBs is 20 log magnitude of this thing, 1 plus j omega on z, where z is a real number. And here it gets harder, because this thing does not look like a y equals mx plus b, because logs don't take sums and turn them into sums. They take products and turn them into sums. And so this plus sign is making things difficult. So the usual workaround is to just speak about this function asymptotically. So at low frequencies, say omega going to 0, the 1 will dominate. So j times close to 0 over z, no matter what z is, I can always let omega get very, 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 very small. And j omega over z will be a very small imaginary number. And so the magnitude of 1 plus a small imaginary number looks like 1. Okay, so this means that the log of 1, well, the log of 1 is 0. So we say that at low frequencies, a first order 0 has close to 0 magnitude. So let's get that sketched. We can do it here. Okay, so we gotta fancy up the plot a little bit. Let's say the 0 is at this location. So z radians per second. Then I want this color. When we are much lower than z radians per second, we have 0 dBs of magnitude. Probably should have color coded that to get the right asymptote, but too late now. Let's say at high frequencies. At high frequencies, and by high frequencies I mean omega much larger than z. Well, then all of a sudden this addition, this sum, looks like a real 1 plus now a very large imaginary number. So this is the idea that the real part isn't changing, but as omega gets bigger, the imaginary part gets bigger and bigger and bigger until finally the magnitude of this vector, it looks like it's pointing just straight up. So we treat the magnitude as the imaginary part, right? Because we're approximating the real part being insignificant in calculating this hypotenuse. Okay, so hey, look, we've got the log of a quotient, which is then the difference of logs. So this is 20 log omega minus 20 log of z. And here's the cool thing. This is the y equals mx plus b story again. So y equals mx plus b. So this high frequency asymptote has a slope of positive 20, and it has a y-intercept of negative 20 log z. Or we could analyze for its x-intercept, which would be solve for the x that gives 0 here. So that would be 0 equals mx plus b. So if I subtract the b over, divide by m. So the x-intercept is 20 log of z divided by 20. So it's just log of z. So that's this point here. So this is a slope of 20 dBs per decade. And nope, it has to pass through. Sorry about that. It has to pass through this point. And I know that it's a valid approximation as omega gets much larger than z. But in this region, we actually don't know what happens. So this is a slope of plus 20 dBs per decade. And this line has to pass through this point with that slope. But again, this line is only, well, it's only asymptotic for all frequencies, but the asymptote is close to the real true graph for large frequencies. So the question is, what happens in between? And I think that in 212, when you learn about Bode plots, they pretty much just say, okay, draw that line, and where they meet, be happy and don't ask any questions. Does that about describe your 212 experience?
That sounds about right.
Almost exactly.
It's like I was there. So let's analyze whether that's valid. It might be true, right? It's possible. We could figure it out if we do a third case. So let's say at omega equals z. So I see these as three cases. Here's the low frequency case, here's the high frequency case, and here's the kind of mid frequency case. Because when omega equals z, that should tell us, is it 0? Is it above 0, below 0? What's going on here? So at omega equals z, then the magnitude of H4 at omega equals z in dBs is going to be 20 log of 1 plus jz over z. I don't have a hip-hop joke ready. I'm sorry. I should have been prepared. The z's will cancel, and I get 20 log of 1 plus j. No omegas. That's fine, because we picked a fixed omega, a fixed frequency. But what's the magnitude of 1 plus j? So go over 1, go up 1. What's the length of this hypotenuse?
1 plus
Root 2.
1 times root 2, right. 1 and 1, so that's a root 2. And so this is then the 20 log of root 2. And this is, there's no reason that anyone walking down the street should know what that is, but there is every reason for an electrical engineer to memorize this number. So this works out to be 3 dBs, or 2.99 or whatever, but everyone calls this a 3 dB value. Okay, so I don't ask you to memorize a whole lot. I mean, everything is pretty much open note. This is something that you should memorize, just to show off to your friends. Okay, so what we've just decided is that the asymptotic lines here meet at z radians per second, comma 0 dBs, but that's not true, because the true value of this magnitude is 3 dBs at this frequency. So we have to be actually passing through that point. Did that erase itself? Yes. So this is 3 dBs up at z radians per second. So I'm maligning 212, and that's not fair, because you can get a long way in estimating frequency responses with the straight line approximations. I won't argue that. In fact, I think that some people, when they learn about these 3 dB corrections, they say, well, I need to be accurate. I need to be as accurate as possible all the time. And that's not true. Sometimes the straight line approximation is all you need, and it's much faster and it's much easier. But if you want a more accurate picture, you need something that follows the high frequency asymptote at high frequencies, but then departs around the 0 location, and then eventually finds its way back to the low frequency asymptote. Okay, so this is a more accurate picture of the magnitude response of a real 0. How did I get this slope? Well, I knew I had to go through that point. I knew I had to approach that slope, and so I am approximating this with a smooth curve. I mean, it is a smooth curve, but there are lots of smooth curves that satisfy this. So you might say that I'm just making it up as I go along, and that's true. However, if I need to know what the gain of this system is around z radians per second, I will be much better equipped to tell you the true gain if I look at the green curve rather than if I look at the blue curve. Does that make sense?
Yeah, so it's kind of like the root locus branches when we're using the bounds of the asymptotes to figure out the curve. Kind of same idea.
Yeah, a little bit like that. It is true. So mathematically, we could show this, that the green curve always sits on top of the blue lines for a 0. For a pole, it's the opposite. But you will never have any crossings like you did possibly have crossings in the root locus diagrams. Okay, so the green curve just sits nicely on top of this little elbow here. And once you get 1 decade above or 1 decade below, they're indistinguishable. Like no one could tell the difference. Okay, it's just in this region where if you need an accurate measurement, use the more accurate method. If you just need something quick and dirty, or if you need something accurate that's far away from the action, then use the easier straight line approximations. Okay, let's talk about phase. So the phase of H4 is the phase of quantity 1 plus j omega over z. Now we're going to do another kind of low frequency, high frequency, mid frequency analysis here. So when omega is much, much less than z, then this phase looks like the phase of 1, which is 0 degrees. So let's get another axis down here. And for frequencies down here, we're sitting at 0 degrees, asymptotically. For frequencies up here, omega much, much bigger than z, then we're looking at the phase of j omega over z, which is again a phasor that points due north. So this looks like asymptotically 90 degrees, positive. Okay. So then the question becomes, what happens in the middle? Omega equals z, then the phase is the phase of 1 plus j, which if we look up here is exactly 45 degrees. So there's no approximations here. We know that this has to pass through this point. Okay, so the common practice is to go 1 decade below the midpoint of the transition or the 0 location and 1 decade above for the asymptotes, and then connect those two endpoints through the midpoint to get the phase picture. Okay. And this is, I don't have a trick for you here. I can tell you that the error here is about 5 degrees. And similarly, the error here is about 5 degrees. That is, by drawing these lines, by drawing them as straight lines, you're missing out on about 5 degrees in the worst case. These are the biggest errors are at the corners here. And so you're going to be off by no more than 5 degrees. And you can do that by just working out what is the phase of 1 plus j 10z over z. And that works out to be about 86 degrees, okay, or 85 and change. Whereas this picture would tell us it's exactly 90 degrees. So 3 dBs is sometimes makes a difference between a good filter and a bad filter. 5 degrees, it could be important. And if it is that important, I suggest you use a computer to help you plot these. But as far as I can tell, being off by 5 degrees in a hand sketch hasn't ever really cost me anything. Now, I say that now, and when I get home, I'm probably going to have to draw a super accurate Bode plot. But any questions on this? The magnitude plot is where I wanted to introduce the 3 dB correction. The phase plot, I think that looks like the old phase plot that you're used to. All right. If you can do a real zero, you can do a real pole. So actually, I don't want to spend a whole lot of time on this, but I will give you the final answer. Here's our first frequency axis. Here's our second frequency axis. And if the pole is at p radians per second, then the straight line approximation comes in here at 0 dBs and then leaves here at negative 20 dBs per decade. And the phase approximation comes in at 0 degrees and it leaves at high frequency is at negative 90 degrees. And midway, it's at negative 45 degrees. But if you need to be more accurate, then this truly passes through this point. So we've got the curve approaching up here and the curve approaching down here, passing through negative 3 dBs. Okay. So again, I'm going to refer to these as the 3 dB corrected magnitude or curve, whereas this is what I'm going to call the straight line approximation. Okay. And again, I don't want to beat this horse any more than I have to. Sometimes straight line is good enough. I'll leave it at that. Okay, and the derivations for these are the exact same as the derivation for the 0, except there's negatives. What I want to, well, I guess what I want to start today is this guy. Quadratic poles, also known as complex conjugate poles. They are the ones that we're familiar with, the ones that we are used to writing in this canonical form. Right, if you multiply top and bottom here by omega n squared, you will recover the canonical form that you're used to. I guess also replace the omegas with the j omegas with s's. Okay, so let's talk about magnitude here. If I want the magnitude of H6 as a function of omega, then I'm looking at the 20 log, sorry, dB version, 20 log of the magnitude of 1 over this thing. So here, heads up, this is omega n squared, that's fixed. This is omega squared, that's our variable. So some people miss the subscript, and the subscript is important here. Plus j times 2 times zeta times this fraction again. Okay, so this is the log of a quotient, which means I can pull the negative 1 out. So this looks like negative 20 log. The magnitude of the bottom, but the bottom is a complex number, which means we should be able to use Pythagorean theorem to work out its magnitude. So this would be the root of the real part squared, 1 minus omega over omega n, inside squared and outside squared, plus the square of the imaginary part. So that's the thing times the j, 2 zeta omega over omega n squared. Now, if you like, we can take the radical and we can multiply it out in front. So this becomes a 1 or a 10. And so we can actually get quite a ways with this expression. We can do the low frequency, the high frequency asymptotic analysis. So for omega much, much less than omega n, this magnitude is dominated by, well, you tell me. What term inside the log dominates when omega gets much smaller than omega n?
1.
Exactly. This guy gets tiny. This guy gets small. And so the only one that doesn't change, that doesn't get smaller as omega gets smaller, is the 1. So we're looking at approximately negative 10 times log of 1, which is 0 dBs. Let's flip the script and talk about what happens when omega is much, much larger than omega n. Okay, so now this and this grow, but this one grows faster or grows bigger for any given omega change in omega. You get a much faster or larger growth on this term than you do in this term. So if we're just looking at one term to dominate, it's going to be this one. Okay, so then we're looking at, what does this look like? Minus 10 log of negative omega over omega n, inside squared, outside squared. The outside squared will kill the negative here, so that means we're looking at negative 10 log omega on omega n quantity to the 4, which is where we get our 40 log out in front. And if I take the quotient omega over omega n, I can turn it into a difference, log omega minus log omega n. And there's a negative out front, which distributes and changes the sign of what I just said. Okay, so we've got low frequencies, we've got high frequencies. Let me get myself some more room here. I don't want the line there. I want the line there. I don't want the line there because this is going to be negative. Sorry. I want the line here. Okay, that was an adventure. So let's say that omega n is the relevant anchor point here. Everything is with respect to omega n. So let's sketch in our low frequency asymptote. And then let's sketch in our high frequency asymptote. So this is again y equals mx plus b. And when omega equals omega n, this thing has an x-intercept. This thing intercepts the x-axis. So if this is the 0 dB line, the 0 dB axis, then I get the point with slope negative 40, so 10, 20, 30, 40, through this point. And this asymptote is valid at high frequencies. And we've got a big question mark under there. Okay. Again, in 212, you would have just drawn these two straight lines, perhaps, and called it a day. But we are going to spend actually a significant part of this next lecture resolving this question mark about what happens when these two lines intersect. And to give you a taste of that, we're not going to be able to get too far on it. I want to do the third case. I want to say let omega equal omega n. And then we're looking at, so this is then, there's no approximation here. The magnitude of H6 in dBs is negative 10 log 1 minus 1 squared plus 2 zeta times 1 squared. Okay, so that goes away. And I can pull the square out. So this looks like negative 20 log 2 zeta. Aha. So we have a second parameter. The zeta, if you know zeta, or said another way, you have to know zeta to know where should I draw this point. Yeah? If zeta is 1/2, where does the point go?
Zero.
Exactly. So these lines I just drew, they are all valid. They're all, well, I guess not all of them. I got a little carried away. Oh boy. Spinning circle of death here. I don't know what's going on here. Did I just lose all of that? Sweet.
You can recover in the corner.
Oh, which one do I pick? Which one do I pick? The more recent one, right?
The late, yeah.
I think that's all. I think that's the most recent autosave. Yeah, because that was from 6 minutes ago. Okay. Darn. We had this, we had omega n, and we had 1, 2, 3, 4. We had this. So if zeta is 1/2, then I pass through that point right there. And we had the magnitude of h at omega equal omega n in dBs, h6, was -20 log 2 times zeta. So if zeta is bigger than 1/2, does this end up being like a negative dB number or a positive dB number? If zeta is bigger than 1/2,
Positive.
yeah, so the log becomes positive, but the negative out here makes the entire thing negative. So for zeta's bigger than 1/2, we are somewhere down here. And for zeta's smaller than 1/2, we are somewhere up here. Okay, so we're going to learn next time what makes that happen, what makes this happen, and then finally what makes this happen. Okay, they're all possible and they all depend on zeta. Right, and this, I hope this makes sense to you. I hope that you want this to be true because zeta is our damping ratio. Zeta controls how oscillatory these poles are. You can also think of the more oscillatory the poles are, the more prone they are to resonance. And so that's what we're going to eventually see comes out of this is we get to talk about the resonant frequency of the poles, which is a slightly different concept than the natural frequency of the poles. Okay, so more on that next time. We can close with a few quick questions if you have them.
Can you slow down for the next slides next time, please?
Yeah, the next stuff will be new stuff, so I will explicitly be slower. Today was review, but yeah, for sure.
Thank you.
Professor, I wanted to ask, you had certain start and stop points on the graph, like 10 to the -1 and 10 to the 1?
Which graph?
Well, for a majority of the graphs, you had a start and stop point between high frequency and low frequency. Like there was, yeah. Well, actually, I guess you didn't. Well, when is the curve stop and start, or is it just continuous at some point?
So there's no discontinuities. Everything is a well-connected curve. Whether there's a kink or not, it depends on which version you're going to do, the approximation or the 3 dB correction. Maybe what you're talking about is the fact that this green and this blue kind of started to merge up here. And yeah, that's kind of my guideline, is 1 decade above. In my experience, these two curves are nearly the same. And 1 decade below, they're certainly the same.
Okay.
So I tend to start the divergence for the 3 dB correction 1 decade below and terminate at 1 decade above.
Okay, because like even on the graph below that with the phase angle, it's pretty apparent that there's a point where you just start transitioning to a line with a slope.
For sure, and that is a much more well-developed theory. Is that this is always z over 10, and this is 10z.
Okay.
And that's because this 5-degree error is acceptable to whoever started these sketching rules. In truth, this is not a kinked curve or a kinked line. This is a smooth curve. In truth, it asymptotically sits on top of 0 here. It passes through 45 degrees, and it asymptotically approaches 90 degrees from below. So the true curve is closer to what I have in black here. But this gap, like I said, this gap is no bigger than 5 degrees on either of these corners, so you might as well draw them as corners.
Okay.
Cool. Thank you, everyone. Sorry for the PowerPoint snafu. I will see you on Friday.